Stop logging your load balancer's IP address as your client IP. I see this mistake in production systems every single week, and it completely breaks your security auditing, rate limiting, and fraud detection.
Wait, that sounds serious. What do you mean the load balancer's IP gets logged instead of the actual client?
Hey everyone, welcome back to the Network Ninja Cloudcast. I'm Marcus, and with me today is Priya.
Hey Marcus, really curious about this one because I've definitely seen weird IP addresses in our application logs.
Perfect timing then. Today we're fixing that exact problem with Proxy Protocol v2 on AWS Network Load Balancers.
So what's actually happening here? Why would my app see the wrong IP address?
Here's the deal, and this is important. The behavior depends on your target type. If you're using IP type targets with your NLB, your application sees the connection coming from the load balancer's private IP, not the original client. But if you're using instance type targets, client IP preservation is actually enabled by default.
Oh, interesting. So this isn't a universal problem?
Exactly. Think of it like getting a package. With instance targets, the original sender's address comes through. But with IP targets, it's like the package was forwarded through a shipping hub, and the return address shows the hub instead of the original sender. This also applies in certain cross-zone or cross-VPC scenarios.
That's frustrating for IP targets then. So if someone's attacking my application, I'd see my own infrastructure's IP in the logs?
Right. Specifically with IP type targets. You'd see something like 10.0.1.47, which is the private IP of the load balancer node, instead of the actual attacker's public IP like 203.0.113.55. This breaks geo-blocking, rate limiting by IP, compliance logging, everything.
Okay, so how does Proxy Protocol v2 fix this?
Proxy Protocol v2, defined in the HA proxy specification, prepends a binary header to every TCP connection. This header contains the original client IP, the client port, the destination IP, and the destination port. The structure starts with a 12-byte signature, followed by 4 bytes for version, command, family, and length fields. Then comes the address block, which adds another 12 bytes for IPv4 or 36 bytes for IPv6. So you're looking at 28 bytes minimum for an IPv4 TCP connection, or 52 bytes for IPv6.
So the NLB adds this header automatically, and my application reads it?
That's the key insight. You enable it on the NLB target group, but your application or proxy must explicitly support parsing Proxy Protocol. If your app doesn't understand it, it sees garbage bytes at the start of every connection and breaks completely.
Oh wow, so you can't just flip a switch and walk away.
Absolutely not. Let me walk you through the correct setup. First, in the AWS console, go to EC2, then Target Groups, select your NLB target group, click Attributes, and enable Proxy Protocol v2. The attribute is called proxy_protocol_v2.enabled.
And then I need to configure my application to read that header?
Right. If you're using Ginks, you add proxy_protocol to your listen directive. So it becomes listen 443 SSL proxy_protocol. Then you set real_IP_header to proxy_protocol and set _real_IP_ from to your VPC CIDR, like 10.0.0.0 out of 16.
What about other applications? Not everyone uses any Ginks.
HA proxy natively supports it with accept proxy on the bind line. Apache has mod_remote with remote proxy protocol on. For Node.js, there's the Proxy Protocol JS package. Most modern reverse proxies and web servers have support, but you must explicitly enable it.
Let me make sure I understand. The NLB wraps the original client IP in this binary header, sends it to my target, and my application unwraps it to see the real client. Is that right?
Perfect summary. And here's a critical detail. The Proxy Protocol header is only sent once at the start of each TCP connection, not with every packet. Your application reads those first bytes, extracts the client info, then processes the rest of the stream normally.
What's the biggest mistake people make with this?
Number 1 mistake is enabling Proxy Protocol on the target group but not configuring the application to parse it. Your app receives what looks like corrupted data and either crashes or returns errors. I've seen entire production deployments go down because someone enabled this without updating the application config.
So you need to deploy the application changes first, then enable it on the NLB?
Exactly. Deploy your application with Proxy Protocol parsing enabled but optional, verify it works, then enable it on the target group. The second big mistake is forgetting that Proxy Protocol v2 is supported on NLB target groups when the protocol is TCP or TLS, but it's not supported for UDP traffic.
Good to know. So let me recap. Proxy Protocol v2 preserves the original client IP through the NLB by adding a binary header. This is especially important for IP type targets where client IP isn't preserved by default. I enable it in target group attributes, configure my application to parse it, and deploy the app changes before enabling the NLB setting.
Nailed it. One pro tip: always test this in a staging environment first. Use TP-dump on your target instance to verify you see the 12-byte signature that starts with 0 by 0 D0 by 0A0 by 0 B0 by 0A0 by 00 by 0 D0 by 0A0 by 510 by 510 by 490 by 540 by 0A. That confirms Proxy Protocol v2 packets are arriving correctly.
This is going to fix so many logging issues for us.
That's it for today's episode. If you found this helpful, please hit that like button and subscribe to the channel.
And share this with anyone struggling with client IP preservation in their load balancer setup.
Thanks for watching the Network Ninja Cloudcast. See you in the next one.